Hello and welcome. Today, we're diving into something pretty amazing: how factories are teaching their machines to talk. Not with words, but with data, a language that can warn them, hey, I'm starting to wear out, long before a tiny problem becomes a massive shutdown. Let's get right into it.
So this right here, this is the core question, the big one that keeps factory managers up at night. Because preventing a failure isn't just about saving one little part. It's about protecting the entire production line from chaos, from wasted money and time. And the answer, well, it involves giving the machines something like a nervous system.
All right, here's our roadmap for today. First, we'll get to the heart of the dull tool problem. Then we'll explore the machine's senses, the cool tech that lets it feel and hear what's going on. After that, we'll see how we turn all that raw data, that noise, into real knowledge. And of course, we'll meet the AI that acts as the doctor in all this. We'll also ask, is it better to check on things now or later? And finally, we'll tie it all together to see how this is building the smart factories of tomorrow. So, let's start with the problem. A dull cutting tool, it's not just a little inefficient, it's a risk. It's the first domino that can knock over a whole line of others, leading to bad products, wasted materials, and just dead silence on the factory floor. That's why standards like ISO 3685 are so incredibly important. It's not just some boring document, it's the official rulebook. It gives everyone a single, clear definition of worn out, a specific number for how much wear is too much. That number is our finish line. But the real enemy here is being caught by surprise. It's the unpredictability of it all. If you have to wait for a tool to actually break, you've already lost the game. You're just running around putting out fires. The whole goal is to switch from being reactive to being predictive. And to do that, the machine has to tell us how it's feeling in real time. And that's where things get really interesting. This is where we give the machine senses. We can actually outfit a tool with a whole suite of sensors that act like its own personal nervous system, constantly sending back health updates while it works. First up, we've got vibration sensors. Now, think about it like a doctor listening to your heart with a stethoscope. These sensors listen to the machine's hum, its rhythm. A brand new, sharp tool has a smooth, steady beat. But as it starts to get dull, that rhythm gets a little off. And as researchers like Sally Etz and his team showed in 2024, those subtle changes in vibration are a dead giveaway that wear is happening. Next, we have what are called acoustic emission sensors. These are like having superhuman hearing. They can actually hear the tool breaking down at a microscopic level. I'm talking about the tiny high-frequency pings that happen when a microcrack forms, way before it becomes a real problem. Research from Solms Group in 2024 showed these things are fantastic early warning systems for both gradual wear and any sudden damage. And then, of course, there's heat. It's pretty simple, right? A dull tool has to work harder, which creates more friction, and more friction means more heat. Temperature sensors give us a direct reading of just how much stress that tool is under. Work by Lapshin back in 2021 and 2022 really drove home how reliable tracking temperature is for understanding tool wear. See, no single sensor can tell you the whole story. It's all about teamwork. The vibration sensor tells us about the rhythm of the cut. The acoustic emission sensor hears the first whisper of damage, and the temperature sensor feels the strain. When you combine them all, a technique called sensor fusion, you suddenly get this really rich, complete health report for the tool. Okay, so we're getting all this data streaming in from our sensors. But here's the catch. A raw signal from a sensor is just a messy jumble of information. It's pure noise. So the next absolutely crucial step is to cut through that chaos and find the meaningful signal hidden inside. And this is how we do it. It's a pipeline. You start with that messy, raw signal. Then you apply some pretty sophisticated signal processing to clean it all up. From that clean signal, you pull out what we call features. Those are the specific patterns that basically scream, I'm wearing out. And once you have those features, you can generate a clear, simple diagnosis. Now, don't worry, we're not going to do a deep dive into the math here. But just so you know, techniques like the wavelet transform are amazing at this. The best way to think about it is, imagine you're listening to a recording of a whole orchestra. A basic analysis might tell you all the notes that were played. A wavelet transform, on the other hand, can tell you the exact millisecond that the triangle was hit. It lets us pinpoint the precise moments that matter inside that sea of data. So once we have that clean, meaningful data, we need a brain to make sense of it all. And that brings us to the AI diagnostician. This is the part of the system that doesn't just see what's happening now, but actually predicts what's going to happen next. And man, The AI toolkit we have today is just incredible. We've got deep learning models that can find these wear patterns all by themselves. We've also got supervised learning algorithms like support vector machines, or SVMs. An SVM is basically trained to draw a line in the data, separating all the signals that mean healthy from all the signals that mean, uh-oh, we have a problem. By feeding these models tons and tons of examples, they get incredibly good at spotting the signs of failure.
So, just how good are they? Well, a recent study from Babu in 2025 showed that a well-trained AI could predict tool wear using just the vibration data with around 98% accuracy. Let that sink in, 98%. That's not just a cool science experiment, that is rock-solid reliability you can build an entire factory's maintenance strategy on.
So we have the technology, but now we have to ask a strategic question. When do you actually use it? Do you watch the tool's health live as it's cutting, or do you pull it off the line and check it afterwards? It's a classic trade-off. On the one hand, real-time monitoring is amazing because it's immediate. You can hit the brakes the second something looks wrong. But you're also dealing with all the noise of a running machine. On the other hand, checking the tool offline with a microscope gives you a super precise measurement. But you have to stop everything to do it. It's accurate, but it's slow.
So what's the answer? Well, it turns out you don't actually have to choose. The smartest way to do this is a hybrid approach. You use those super precise offline microscope measurements to create the perfect answer key. Then, you use that perfect data to train your real-time AI models. That way, you get the best of both worlds, the pinpoint accuracy of the lab running at the incredible speed of the factory floor. All right, let's bring this all home. This isn't just about some cool new gadget. This is about building the next generation of factories by tying this intelligent AI-driven monitoring directly into the standards the industry already relies on. This is what people mean when they talk about Industry 4.0. It's about creating these smart, data-driven factories. We're getting away from the old way of just replacing parts on a fixed schedule or waiting for them to break. We're building systems where the tool itself tells you exactly when it needs attention, letting you use it for as long as possible without ever risking a failure. And that right there is really the key takeaway from all of this. It's about creating harmony between these new real-time technologies and the proven guidelines of a standard like ISO 3685. You could say the standard tells you what to look for, the maximum wear limit, and this new technology tells you how to look for it, continuously and automatically. The end goal, really, is a system where a person on the floor just gets a simple alert on their tablet. Hey, tool number 7 is at 85% of its official wear limit. Time to schedule a replacement. That's it. It takes quality control from being this manual, periodic chore and turns it into an automatic, constant, and totally predictive process. And that leaves us with one last big question to chew on. What does the world of manufacturing look like when every single part, from a huge industrial robot down to the tiniest cutting tool, is smart enough to predict its own future? That's the incredible new reality we're starting to build right now. Thanks so much for watching.